Thank you for purchasing our pre-recorded stream seminar. Please watch the short educational video first before watching the main seminar topic video. Thank you.
The industry's origins in the United States can be traced back to the late 1800s, and more specifically the early 1900s, with the advent of electrically welded steel pipe. In North America alone, about 300,000 miles of these mostly underground pipeline systems transport huge amounts of natural gas each day, serving as the critical link between fuel-producing regions and end users. The pipeline systems continually evolve, being updated with the latest proven technologies as demand warrants or specific area changes dictate. It's more and more commonplace for population and development to grow toward what were once rural pipeline systems. For that reason alone, it's more and more important for all stakeholders to recognize and respect these important underground facilities. One of the leading causes of pipeline incidents is careless excavation practices. Preventing pipeline damage has become a major focus area for operators. Bureau of Transportation Statistics records have historically and consistently shown that long-haul pipelines have the best transportation safety record in the United States. Pipeline system accidents, which are reported to PHMSA, are rare, particularly when one considers the trillions of cubic feet of natural gas transported each year. But the industry fully understands the potential impact of a damaged pipeline and takes many measures to both maintain pipeline systems and prevent these accidents from occurring. The industry has built its solid safety record on a foundation of continuous improvement, and as a result, it has seen a percentage decrease in the number of significant incidents in the past 20 years. While the amount of natural gas moved in that time frame increased dramatically. Every step of the way, these long-haul pipeline systems are monitored around the clock by high-tech equipment and highly skilled employees. The basic process to transport natural gas long distances involves not only the specialized steel pipeline, but related measurement and pressure regulating equipment, compressor stations that compress the natural gas molecules to facilitate the journey, and control centers that monitor major operating conditions around the clock. Companies also repeatedly communicate with those living near pipelines, emergency responders, and other important stakeholders through various methods, while providing strategically located above-ground markers and other means to remind them of their mostly underground assets. An object-free and clearly defined right-of-way corridor is critically important to pipeline companies both during the construction and operation phases. While a temporary workspace width of about 100 feet is generally required during construction, the permanent right-of-way for a long-haul natural gas pipeline is typically 50 feet wide or roughly 25 feet on either side of the buried pipeline. This helps identify the presence of an underground pipeline. On the right-of-way, work site preparation begins with the removal of all trees and brush from the construction work area. Stumps are removed over the width of the permanent right-of-way, with the exception of stream buffers and wetlands. Specialized heavy equipment is often used to assist in this process. Downed timber is often cut into usable lengths or otherwise disposed of after seeking landowner input. Grading is conducted where practical to provide a relatively level surface to allow safe operation of the heavy equipment required to excavate the trench and install the pipe in the trench. A trench is excavated that is wide enough to safely support the depth of the trench and to allow lowering in of the pipe without damage to the pipeline coating or harm to construction personnel. In some rocky areas, blasting will be required to excavate the trench. The steel pipe sections, or joints, in 40 or 80-foot lengths, are trucked to the construction work area and strung out along the route in the areas where they are to be welded together. As necessary, the pipe joints are bent to follow the route of the pipeline and contours of the ground. A specialized pipe bending machine is used. The amount of the bend in the pipe section is limited to avoid damaging the pipe or coating. Once the individual pipe joints are bent to fit the trench, they are welded together into long continuous sections which can be up to several thousand feet depending on terrain. The welding is highly controlled and performed by welders using proven international standards. Each weld made on the pipeline is visually inspected, and the welding process is verified with either radiographic or ultrasonic technologies. Welds that do not pass stringent requirements are repaired or replaced. A specialized corrosion protection coating is applied to each of the weld joint areas after the inspection is complete. The coating on the entire pipe section is then electronically checked for any coating problems and repaired prior to lowering the pipe in the trench. The pipe sections are lowered into the trench by special pipe-laying tractors called side booms. Care is taken to not damage the coating during this process. The pipe is placed in the trench on sandbag benches to prevent damage to the pipe coating. The coating is rechecked again. The ends of these completed pipe segments are then welded together in the trench to form a continuous pipeline. Once long sections of pipe are completely in the trench, the material excavated from the trench is carefully replaced over the pipeline. A layer of rock-free pad dirt is placed all around the pipe to protect the coating. As various sections are completed and the trenches are backfilled, the pipes are filled with water and safely pressurized to a point significantly higher than the maximum pressure the pipe will ever be operated to verify the overall integrity of the pipeline. This test pressure is held for a minimum of several hours to test the structural integrity and overall strength of the pipeline and to allow minute water leaks to be found. The cleanup and restoration process starts as soon as practical after the pipe trench is backfilled and continues until the construction work area is restored and revegetated. All terrain is replaced to original contours as much as possible, and the work area is restored utilizing seeding and soil preparation specific to the affected area to restore ground cover and to minimize erosion. Temporary workspaces will be allowed to return to their previous state, either wooded or open. The permanent right-of-way corridor will need to remain free of most obstructions to signal to any passerby that underground utilities are present. Above-ground markers will be placed at locations such as road crossings and at various strategic places along the route to further indicate the presence of a pipeline. The markers contain important information such as operating company contact phone numbers and the commodity being transported. Upon completion of construction, the right-of-way typically may be used for most residential, commercial, or agricultural purposes, provided this use does not interfere with the safe operation, maintenance, inspection, and repair of the pipeline or obstruct access to and along the right-of-way. Restrictions are documented in the easement agreements, but in general, permanent structures should not be placed on the right-of-way. Some examples of these types of obstructions include houses, decks, sheds, pools, and septic tanks. Also, tall vegetation or trees should not be placed on or near the right-of-way. Some items, such as driveways, fences, and improved parking lots, may be placed over and across a right-of-way if they meet certain requirements to protect the pipeline. Always check with the pipeline operator and easement restrictions prior to beginning any work.
And here is more educational videos on the subject.
Pipelines are the safest and most efficient way to transport energy. Crude oil, gas, and petroleum products are all transported via thousands of kilometers of pipelines across the world. Pipeline owners and operators work to prevent pipeline failures by evaluating, inspecting, and maintaining their assets using integrity management programs. One element of integrity management programs is pipeline inline inspections. Conducting inline inspections with gauges or tools, commonly known as smart pigs, using the magnetic flux leakage technique allows pipeline companies to safely check for external and internal defects, dimensional abnormalities, and corrosion in pipelines. Utilizing these tools to examine the structural integrity of pipeline systems can protect workers, the environment, and surrounding communities. Intertek helps companies remain compliant while assuring asset safety and reliability. Intertek's Pipeline Integrity Management Team, supported by a strategic technology partnership with USA-based Q Inline, uses state-of-the-art inline inspection tools that are designed to meet the most challenging inspection needs. Through our partnership with Q Inline, we are committed to providing a high-level service and continuously developing new technologies, utilizing their extensive knowledge and experience to provide this service to pipeline companies in China. Our personnel are well-trained and have been qualified by Q Inline in the USA to serve our clients locally in China. Our equipment is located and maintained in China for ease of scheduling around planned pipeline inspection windows. Pipeline inline inspection tools are intelligent by design and rely on magnetic sensors, expandable dimensional inspection calipers, and GPS or alternative location devices to map data when performing inline inspections on pipelines. The sensors provide technicians with valuable data that can be analyzed to determine abnormalities or weaknesses in the pipe and identify any potential safety hazards. The data can then be used to determine whether repairs are needed or whether a section of the pipeline needs to be replaced. The inspection tools are deployed into the pipeline using devices called launchers. The launcher is connected to the main pipeline and can be isolated from the main flow of product. The launcher is drained and the inspection tool is loaded through a hatch at the end of the pipe. The pipeline product pressure pushes the tool through the pipeline to gather data at varying speeds depending on the pressure in the line. The inspection tool works by using high-powered magnets to create a continuous circuit within the pipe wall to detect magnetic flux leakage. Magnetic flux leakage is a magnetic method of non-destructive testing during which powerful magnets are used to magnetize the pipe wall. When the inspection tool encounters an abnormality such as excessive corrosion, a change is detected in the magnetic flux patterns, which is detected by the sensors and stored within the tool for evaluation once the inspection is completed. After the tool has completed its journey through the pipeline, Intertek technicians download the data from the tool for evaluation. The data is analyzed to determine if and where repairs need to be made. Technicians can provide feedback by selecting and prioritizing indications that need repair to make sure customers are compliant with industry standards and regulations.
Good morning. My name is Franco Davati, and I'm the president of Failure and Damage Analysis in Houston, Texas. I'm a professional engineer and have been working as an engineer for the past 35 years in the engineering industry. Half of my career, I worked as a failure analyst in aerospace, oil and gas, and automotive industry. And the other half has been in accident reconstruction and investigation. And since 2003, we have been giving these continuing education courses in failure analysis, forensic engineering, not just for professional engineers, but also for attorneys as CLE and continuing legal education. So we decided to develop a series of courses which would be much easier for the users. We have always been giving our courses as a live seminar, but we decided it would be better if this method of recorded live streaming, as you may want to call it, for easier use of our customers. We are going to develop a series of these courses, for online courses that you can watch, and today is one of them. And the topic of today is the New Mexico pipeline explosion. As we are going through the course, if you have any question, you can write it down and email it to us, and you will get a response within 24 hours after the course. In the case for New Mexico pipeline explosion, the accident happened in the summer of 2000. A family of 12 was vacationing in the banks of Pecos River in New Mexico. Suddenly there was an explosion and 10 members of the family passed away, died as a result, and the other 2 were in critical condition. And the police was called to the scene of the accident, and they wanted to see what caused the accident in the area. So, as the state police did not know if this was a mere accident or it was some kind of a sabotage. The accident site was, as you see, was pretty much baked, and it seemed as if there was a bomb was thrown in the area. There was a big crate, and as they saw, there was a pipe explosion in the area. So they contacted the local gas company to see if they have any of what's going on, any idea. The extent of damage was so much that the heat from the flame had melted all the windows and all the rubber plastics on the vehicles. But yet there was no sign of where did the ignition started in the area. We have another course in fire and explosion that you can also see that you can always usually identify where is the origin of the explosion or the fire, and then follow the pattern how it has propagated through the area of the accident. But in this case, the investigators were baffled that they couldn't find what had caused it. They thought maybe if the source of ignition had came from a campfire, or even if the family were grilling something, or had it been caused that the gas had seeped through and escaped somehow through the pipeline. And so they did an aerial investigation. There was no sign of such a thing. There was no sign of dead vegetation or any sign that the liquid gas had escaped the pipeline. And they couldn't even find any source of ignition in the site. They also couldn't find any point that if part of the ground had been dug, if there was a bomb had exploded, if any of the gas tanks of the vehicles have exploded. There was not any sign of that neither. After less than 24 hours, when they couldn't find it, when they talked to some of the authorities, they decided that the accident had happened at the pipeline number 1103 that was exploded. This line carries natural gas from Texas all the way through New Mexico, Arizona, and to California. The line had to be closed, and since it goes thousands of miles, every 70 miles they had a pumping station in order to pump the gas through the pipeline. They couldn't know they didn't know if maybe there was too much pressure in the pipeline causing a rupture in the pipe, or had it been any damage in the pipe along the way. This was a 30-inch diameter pipe, which is very normal that they use for the liquid gas, when they are transferring it across the country. When they contacted the company or some of the pumping stations, they did not see any problem or any trouble, anything that shows any discontinuity in the flow. And what had happened is, once going back, somehow at some point in that area, the gas had seeped through, and once the natural gas had mixed with the air and the ratio was correct for ignition, it had ignited and the big tower of explosion had happened. Interestingly, as they were gathering information, some of the scientists 200 miles away, they were able to come up with some data that showed the time of the accident and the explosion. What happens is, the seismometers, they record any movement on the ground. When there is always ground is shifting and movement. When they measure these movements, they can show these movements in the form of a voltage. And so when they were looking at a typical day that they would see, suddenly they saw a pattern that showed unusual, as there was no seismic activity in that area for the past couple of days. When they were examining, they were able to see the exact time that the first ignition had happened, and then the explosion, and then the second explosion that had happened in the area, and the length of the time that the fire had burned. So with that data, they were able to justify and say at least the time of the accident as it went. Also, they were trying to figure out what caused the pipe to burst. That was somewhat of a mystery. The accident had happened at 5:26 a.m. and the pipe, when it ruptures, it does not burst into flame right away. The liquid has to mix with the air, and when it's the right ratio, then it can cause an ignition. What has happened is, once the gas had seeped through, it was just like a rocket that is laying on its side, and the gas is starting to flowing, and then it starts mixing with the air as it dissipates through the air, and at the right mixture, suddenly the gas can ignite. According to the data, 24 seconds after the pipe ruptured, the mixture had ignited. But the ignition source was still unclear. They couldn't tell if this was happened right at the accident site, maybe if there was a campfire or a grill was open and they were doing some cooking, or simply there was some kind of a spark somewhere, or it could have been caused as a result of the pipe by the electricity. Just if it's a static electricity, once the pipe has exploded and the gas is flowing outside, then if there is some part is rattling and along the flow, some broken piece, and causes a static electricity. Uh, this would have been once it ignites, it would ignite the gas. So for that, they contacted National Transportation Safety Board. National Transportation Safety Board, they decided to investigate the accident, and when they sent their team, there were thousands of miles of pipeline in the country, and they had to shut down all of them until they figure out what had caused this accident. As many people could have been in danger. The senior metallurgist went to the site of the accident to do an on-site inspection, and they realized that the pipe had been broken in 3 separate pieces. The largest piece was tangled in the power lines. That just shows some about the strength of the explosion and how far the piece had traveled. So they decided to take some of that sample, and they take it to the lab at the NTSB and examine it in order to find out what had caused the explosion. Earlier, before starting this program, this video, we tried to show, in order to educate some of the engineers or attorneys who are watching this program, the basics of pipe laying and pipe laying on the ground, how it's done. And we also showed some inline inspection that is done by the so-called, they call it PIG, that basically just because of the noise that it makes as it travels through the pipe, which is designed to inspect the pipe as it goes through and gathers the data and all 360 degree around the pipe as it shows if there is any sign of a ding to the pipe, if there is a thickness of the pipe have been reduced, or if there is any corrosion on the pipe. It allows it to gather that data and send it back. Usually a pig can travel about 5 miles per hour for every 2,000 feet, or until they gather the data. Hopefully we were able to see those videos as a part of the educational program, so we understand this investigation a little further as we go. So in a typical pipe laying schematic, as you see during the time to time, they have to bend the pipe with a pipe bending machine in order to contour the lay of the ground. And this bending of it, they usually do it at the site, and there are different ways and different machines that they were doing it. This pipe had to be bent at the time that it was being installed. If they do it somehow in the factory, there are some areas that they put when they are on the field or in the lab, they put what they call a wrinkle on the pipe. So when they are bending it, it has a room for bending, which also can cause some problem, because at the site they have to inspect it to make sure there have not been any crack in the dam where it has been bent, or they also have to inspect for any ding damage. Usually if the pipe is hit by a tractor or a bulldozer, that ding can cause a crack that can grow later on. So for this pipe, at the time when they were laying it, because of the contour of the area, the pipe had a bend in the middle of it. Anytime that there is a bend in the pipe, that it has to sag, that can cause problem, because the reason is it will cause condensation as the natural gas is going through it, and it can cause a pool of water at the bottom of it, which that water can later on cause corrosion, and once the corrosion starts, it's going to eat through the thickness of the pipe and causes a rupture. The pipe had been installed 50 years ago. Now the length of the 50 years is not that important, but the maintenance of the pipe during this time is the important part. So when the investigators were examining the remaining of the pipe, they noticed a slight bend on the upper section of the pipe. So it had a low point as when they were installing it, and that low point can gather water, a trough of water underneath it. But these are usually found out when you run the pig through the pipe, and if there is any area, usually it can clean it. If it cannot clean it, it has to be able to report it. As they were going through the broken pieces, they were cleaning up, and they saw some signs of what is called chevron. Chevron are pointy signs on the sheared area of the failure that points to the direction of where the rupture has been as the metal had formed. So what they did is, these are the shape of the chevrons. So they did a scan using a scanning microscope. They examined the entire area, the area that had failed. And when they look at the fracture face, they also, besides seeing the chevron signs where it point where the rupture had happened in the pipe, they were also saw some parts that the pipe had been pitted, a series of pitted points, and that the corrosion had eaten through the pipe. It had not completely gone through, but it had reduced the thickness enough in order to cause the rupture in that pipe. So the thickness area were measured that caused the failure, and they also noticed that here is an example of it, as the pipe goes through, how the water can stay on the bottom of a bent pipe, and it can pool underneath, and this is what can cause the corrosion in the pipe. Now the question is, what had allowed for this corrosion to start and happen, and how many other cases like this is currently in the pipeline system all across America? And that had to be, these are thousands of miles that had to be inspected. So NTSB, they had to examine 300 miles of pipeline that they were carrying this, and try to see at least all the ones that they had a low point area had to be examined. Once the water is gathered underneath, it can cause a chain reaction. And a chain reaction would be the corrosion, the reduction, and the corrosion eating through the thickness of the pipe and reducing the thickness of the pipe, which eventually it's a pressurized system and would cause a rupture. And it would be a ticking bomb at that point. As they were examining the broken pieces, they also found a high concentration of chloride in the sample, and also This is a more close-up view of the examination that they did in the failed area, the chloride. They also found some traces of microbial life in the area. But the most important part, the 80% of the cause of it was corrosion that had ruptured the pipeline and caused the explosion. Earlier, before this video, we showed that how the pig works in the lining system. I hope you had a chance to see that. Again, here is the example of it, and that it can detect once it goes through the pipeline, it can detect the thickness of the pipe, any sign of corrosion or any dig damage. Now, here is the broken pipe that they had found, but in a typical, when a pig goes through it, for example, when it sees something like this, that's usually about 1% of the dent damage, on the pipe that it has detected and reports it back with the computer. A larger piece would be like this. This is approximately a 3%. On a typical pig, that it has a diaphragm in front. As it moves, it pushes, if there is any water residue or a sludge, down into the pipe, and if it detects any kind of dent or corrosion or reduction in the thickness, it will report it. Now, the place that had happened was, this area that you see is about 300 feet before where the accident had happened. When the pig travels through, when it gets to the sharp angles, of course it cannot go through, so they will take it out. But the way this was designed that the gas comes through and the pig pushes all the sludge and everything at the bottom, that in order to store it, and the gas goes and flows on top and continues. Then this area that it's supposed to hold all the sludges get siphoned off later to another tank and is removed. As you see over here, once it comes over here, the continuation, the pipe goes through, and all this sludge and water and everything is supposed to gather over here, and then it gets siphoned off to the drip tank and removed. So the line gets cleared, and as the gas goes through, it continues. But when they were doing the investigation, they realized that this section that was supposed to hold all the sludge and get siphoned off was 70% clogged up. As a result, the gas that had come through, they had pushed all the sludges without going here along in the pipe, and had pushed it through, and later on when it gets to the lower edge, when the pipe bends, all the sludge had gathered in the bent part in the lower section of the pipe where it exploded. Here is another view of it. That's where they receive the pig, but the gas starts continuing on the bottom as it flows. Here's the maintenance section as it pushes all the maintenance section, but this section is getting all filled, and it's supposed to take all the sludges out. Okay, so here we have, this is the section that as it's come through the maintenance strip, it's filled up. As a result, it comes over here, this is all plugged up, so the sludge does not go over here, and it continues with the flow of the gas, goes down the line. I think it should come in a minute. There you go. This shows the diagram of, instead of depositing the sludge, because it was plugged, it was pushed down the line and went and got all pooled at the bottom of the portion that the pipe was bent. And this is where all the sludge and water had pooled as the pressurized gas flow overs it and cannot push it forward, and they form a trough on the bottom of the pipeline. Now the entire line was shut down, and the inspectors examined 60 other low points that it was along that line in order to get it clear. And after that, in December of 2002, President signed the Pipeline Safety Act, which required all the pipeline companies, they examined half the pipelines by the year 2007, and the remaining were supposed to be finished by 2012 as a result of this. So all the lines have been inspected by the pig, as we know, we showed it before, the inline inspection. And 9 months after the accident, the pipeline 1103 was opened and operational at a lower pressure to make sure everything is going good under reduced pressure, and so it's working up to now. Most periodic test has been mandated by all the companies, especially as the cities are growing. The number of pumping stations are growing around towns, but people are more aware of some of the dangers that might be in their area, wherever they live, or they fish, or they go traveling. We will see the signs of high pressure gas line in the area that we live in or we pass by. So people are just more aware of it. And we also need more and more engineers and failure analysts in order to make sure the safety of the pipeline and the people who live around it. Hopefully you enjoyed this presentation and the cause of the accident of the New Mexico pipeline. And if you have any question, please feel free to send us an email and we will respond to you. And that's the end of today's program. Thank you very much. Hello, and thank you for watching our webinars, our streamed webinar. Now you can go ahead and take the quiz, and after passing the quiz, you can print your certificate. I'd like to mention that our webinars are 100% money-back guarantee, that if the state board does not approve it for any reason, you'll get 100% money-back guarantee. Our streamed webinars are in compliance with the presentation requirements by the State Board of New York, Iowa, Ohio, Wisconsin, Illinois, and Nebraska. The New York engineers must take this streamed webinar between 9 a.m. until 4 p.m. During the week, Monday through Friday, but the rest of the states is on their own. There is no requirement for those times. There is no open microphone during the webinar, very much like any other company who provides this kind of service. All the correspondence and interactions are done via email. All of our webinars satisfy Wisconsin, Iowa, Nebraska, and Illinois live training requirement. Ohio Board of Engineers require a short quiz after the webinar, and all of our streamed webinars have a short quiz after them, which is perfect for the engineers in Ohio, and it also verifies the attendance of the engineers during the webinar. Thank you very much. If you had any questions, please feel free to send us an email. Thank you for purchasing our course.